This revision video is for the Wits University course Introduction to Material Science and Engineering. In today's video we will be looking at phase diagrams and very briefly how we interpret them and what information we can get from them. Okay, here is a phase diagram for a copper-nickel alloy. So we would start off with copper on this side and nickel on that side, and as the amount of nickel that we add increases, obviously the percentage weight of it increases along this axis here. Now, before we carry on, I just want to point out that I created this phase diagram in Excel, so it's perfectly fine for education purposes in terms of explaining how phase diagrams work. However, if you were going to need a phase diagram for copper nickel for a practical application, I would go and consult the relevant reference book. Okay, so in my phase diagram, I have three regions. The first region is my liquid region, which is this region here, right? So in this region, all of the material is liquid, and by liquid we mean it's a molten metal. It's a molten metal that is a mixture of copper and nickel. And we see that we have another region, which is the region below this line here, and in this region our material is all solid. Once again, it's a solid material consisting of some combination of copper and nickel. And then in between these two areas we have this region here, and we call this the freezing region. And in this region we have a mixture of solid and liquid, or alpha and liquid, right? So what we can see from this diagram is that the phase diagram is divided into these three regions by two curves. This top curve is called the liquidus line, and it basically tells us at what temperature above which the material will always be liquid for a given composition. Similarly, this line at the bottom here is our solidus line, and it tells us for a given composition at what temperature the whole of the material will be solid. Okay. Now, we call this diagram an isomorphous phase diagram, and it's actually a binary isomorphous phase diagram. Now, the reason we say binary is that there are two elemental compounds involved, nickel and copper. So that's where the binary comes from. The isomorphous refers to the fact that in this diagram there will always be, I'm just going to change the color here, there will always be 100% solubility. Okay, and that means that no matter how much nickel I add to my copper, I will always, on solidification, I will always have a single phase resulting, right? I'm not going to have a second phase, I'm not going to have a precipitate, I'm going to have a single phase, which will be a combination of nickel and copper. And no matter how much nickel I add to my copper, I will have this 100% solubility. And likewise, no matter how much copper I add to my nickel, the same thing. Okay, so we now have a better understanding of the regions of our phase diagram. Now we're interested in terms of what can this phase diagram actually tell us. So let us look at a 40% nickel, copper nickel alloy. So I'm going to draw an isopleth here. I'll try and draw it straight. Okay, there's my isopleth. Okay, so I'm going to choose a temperature. I'm going to choose the temperature of 1,300 degrees, which puts me right here for that composition alloy. At this point in my diagram, what do I know? I know that my material is 100% liquid, and I know that the composition is 40% nickel. Okay, so that is the composition of the liquid. Let me take another point. I'm going to take 1,200 degrees. At this point, I know that my material now is 100% solid. I know that because I'm below the solidus line. I'm sitting below it. And my composition of my alloy at this point will be 40% nickel. So it's a copper 40% nickel alloy, which is also the same as saying a 60% copper, 40% nickel alloy. All right. So far, that's pretty simple. So the question becomes, what happens if I happen to be sitting here at this point? Okay. So let's say this temperature is about 1,250 degrees. Okay. Now, what is happening at this point? Now, we can see that this is in the freezing range. It's sitting between the liquidus and the solidus lines. I'm in this region. Okay. So because I'm in this region, I know a couple of things. The first thing I know is that I'm going to have a solid and I've got liquid, right? The question becomes, what is the composition of the solid and the liquid at this point? And the way that I find that out is that I draw a tie line. So I go across here at 1,250 degrees. I draw it all the way across here. And then I see at what point does my line cross my liquidus curve. And I say, okay, cool, it crosses it here. And I take a point down. And I get to the point on the x-axis and I say, okay, what do I think the composition is at that point? And I say, it's probably about 32%. And what this is telling me, it's saying at 1,250 degrees for a copper 40% nickel alloy, I will have two phases, a solid and a liquid. And at that temperature, the composition of my liquid is going to be copper 32% nickel. Similarly, I can now go and I can see, where does this tie line cross my solidus curve? And I say, okay, cool, it crosses it there. I do the same thing, I extrapolate down. And I would say, okay, it's sitting at about 45% nickel. And that would be the composition of the solid at that temperature. And I would say, okay, the composition of my solid is 45% nickel. All right, so already I now know that at this temperature, for that composition, that alloy composition, I can determine what the composition of each of the phases are. So still looking at my copper 40% nickel alloy. So I'm still here. What other information can I find out about this this alloy? So what I would really like to know is, if I'm sitting at 1,300 degrees, I'm sitting here at this point, I'd like to know what temperature does my alloy start to solidify. Now, I know that anything below my liquidus line will start to solidify. So as soon as I am below this line, solidification starts. So if I've got a 40% nickel alloy, I know if I'm sitting just below the line here, just below that point there, I know that solidification is going to start. So that's, and by solidification, I mean I'm going from a molten metal or a liquid metal to a liquid and a little bit of solid is starting to form, a small bit. Now I want to know what temperatures does that small little bit of solid start to form. And I do that, I go and look at my isopleth again, which is this vertical line, 340% nickel, and I know I'm there, and I cool down, and where I hit my liquidus line, I now take across, and where that crosses my temperature axis, I work out the temperature, and I would say that the first solid starts forming at approximately 1280 degrees Celsius. And now I can ask a further question. I can say, what is the composition of the first solid? And how do I determine that? So once again, I take my tie line. I know it starts at 1280 degrees, so I draw my line across. I continue until I hit my solidus line, which is over here. And if I, once again, extrapolate down, it looks to me as if my first solid is going to have a composition of 52% nickel. Right, pretty simple. So now I can also say, what is the composition of the last liquid to solidify? So now I'm saying, okay, cool. Pretty much all of the liquid is solidified. There's only a little bit left. What is that composition? So now I need to say, okay, so below my solidus line, so I'm going to say anything below this line here, I'm going to have solid. Which means that if I want to work out what the composition of the last liquid to solidify is, I need to find out where on that isopleth would I have 100% solidification. And that would be where that isopleth crosses the solidus line at this point. And now I do the same thing. I need to know, okay, what is the composition of the liquid? So I need to cross the liquidus line. So I take my tie line and I move across this way, and it crosses my liquidus line about there. And once again, I'm going to extrapolate down, and I'm going to say, okay, it's about 27%. So the composition of the last liquid to form is copper 27% nickel. And what temperature did that occur at? I'm going to once again carry on extrapolating my tie line and see where it crosses my temperature axis. And I'm going to say it's about 1230 degrees. Okay, so this is at a temperature okay. So now we know that the temperature just when the first solid starts to form is about 1280 degrees C. And the temperature where the last liquid starts to solidify is 1230. And interestingly enough, that range has a specific name. And we call it the freezing range. So the freezing range for a copper 40% nickel alloy is 1230 degrees Celsius to 1280 degrees. And this tells us that between this range, our material goes from a liquid to a solid. Okay, so we now know that our phase diagrams can tell us the freezing range for a given composition, where solidification starts and finishes. We can also figure out the compositions in certain region of the curve for certain phases. And the last thing we can figure out is how much, or the weight percentage of different phases. So let us take a 40% copper nickel alloy again. We know that this is our isopleth running like this. And what I'm going to do is I'm going to start off with the easy one. So now I want to know how much of a phase. So if I'm sitting here, how much phase do I have? I've got 100% liquid. And if I'm sitting here, how much do I have? I've got 100% or solid. Okay, and I know what the composition is because at both of those points, it'll be the composition of the alloy. Composition we started with. Now, I'm going to say, oh, well, let's say I'm sitting here. So let's say I'm sitting at 1270 degrees Celsius. Right. So at 1270 degrees Celsius, I want to know how much liquid and how much solid do I have. All right. So in order to figure this out, if I want to figure out how much of a phase there is, I use the lever rule. Okay? Oh, not ruler. Lever rule. So how much solid and how much liquid do I have at 1270 degrees? Okay, if I want to use the lever rule, the first thing I need to do is I need to draw my tie line. Okay, so where does my temperature line or my vertical line cross the liquidus? Let's say it's about 37%, right? And where does it cross my solidus? About 50%. Right. So I now know the composition of each of my phases. I know that the solid's got about 50% nickel, and I know that my liquid's got about 37. Okay. Now I'm going to use the lever rule. So I need to draw my lever. So I'm going to go from my liquid side, which is 37%, and I'm going to draw it across until it meets the base composition of my alloy, 40%. And then I'm going to extend that tie line until I hit my solidus line. So if we look at this diagram, it's the same thing. There's my solidus, there's my liquidus, and this is exactly what I've got there. Right. Now, intuitively, if I look at this diagram, at this point, I've just started solidification. So therefore, I would expect there to be more liquid than solid, intuitively. And when we do this lever rule calculation, we'll find out that that's true. Now, the easy way to figure it out is when I'm doing the lever rule, I always look at the opposite arm of the lever. So if I'm on the liquid side, I look at the solid part of the lever, and if I was on the solid part of the lever, I would look at the liquid part of the lever, right? And if I do that, I can see that this part of the lever is much longer than that part, which would mean that I should have more liquid than solid, and we'll see that now. So in order to use the lever rule, what I do is I take my maximum solid composition, I subtract my base alloy composition, and I would divide it by the total length of the lever, and that gives me a value of 0.7692, which is 76.92%. So what I've calculated is that the percentage weight of liquid at this point, 1270 degrees, is 76.92% liquid, which means that my amount of my solid must be 23.08%. Okay, and that's what I expect looking at this lever. So let us now take another point. Okay, I'm going to choose now 1250 degrees. Okay, and now I want to do the same question. What is the composition? What are the phases present? What is the weight percentage? So, once again, we draw a cross for the same alloy. Sorry, my line went a bit skew. Now I'm sitting about here. So, once again, I'm in the freezing range. So I know that I've got solid and I've got liquid. And I'm going to extrapolate again. And now I'm going to say that I'm sitting, it's once again a very skew line, that my liquid's about 32% nickel, and my solid is about, let's say my solid is about 45. Okay, so there's 45, 32. Now, I've figured out what phases are present at 1250 degrees. I've figured out what the composition is. Now I want to know how much solid is there and how much liquid. And once again, I use the lever rule. So, let's take the solid this time. So I want to work out the weight percent of my solid. I'm going to say, I'm looking at the opposite side of the lever. So I'm looking at this part of the lever now. I'm going to say my base alloy composition is 40 minus 32, which is the composition of the liquid, divided by the total length of the lever, which is 45 minus 32. And that is equal to, which is, therefore, I've got 61.5% solid and 38.5% liquid. Okay. And that is how we use the lever rule to work out the composition and the weight percentage of different phases on a phase diagram. This technique would be the same technique that you will employ on all the other phase diagrams, no matter how complicated they get.